Hello everyone, here is another project in which I will talk about the critical grid emergency where voltage collapse appear. So how and why voltage collapse appear here in this MATLAB simulation. We just consider IEEE 33 bus system, and I just increase the load on this bus system by 3 times. So that's why in normal case here you can see the voltage collapse. So the normal case when our load is triples, the voltage profile is shown by this black line, which is the minimum voltage appear here is 0.5, roughly 0.56. And the next one, which is the second scenario, this is the old way where when the load on our bus system increases, we have to do the load shedding, where we have to cut power to the customers, so our voltage remains above the safety target. So here our safety target, which you can see here, the blue lines which represent 0.9 per unit voltages. So this is the safety target. We have to keep our voltages above this safety target, and if we are fail to keep the safety target, then we may suffer voltage problems, or we may even have to suffer the penalties. So that's why it's very important to maintain this safety target. So by load shedding, which is the very old method, you can see we have maintained above 0.90, but here on 31, 32 and 33 buses, we are below our safety target, and we have to cut powers to many of our customers. Here in this figure you can see that all the red bars which you can see, we have cut power to our customers. So on bus number 2 we just cut 81.3 kilowatts. So this is kilowatt chart, and here on the bus number 30 we have to cut 600 kilowatts to maintain this red line curve. And the smart way here which we are going to adopt, and which I will show you in the MATLAB program, is using the EV fleet for voltage support. So I already made a project on how EV fleets are work together, but right now in this project I'm not going to go very deeply into the EV fleets. Right now we are using a fixed size of EV fleets which will act as a backup support for our voltage support. So EV right over here is just have to support the power. So right now this is the scenario A, which is the scenario 2, which is scenario 2, and this is scenario A here. So in this case we serve our 3.9 megawatts, and we have to shed 7.2 megawatts to maintain our voltages above the safety target. And this is the scenario B, where EV support is involved, and we have injected 7.6 megawatt into our grid using the EV fleets, and our full load served is 11.1 megawatt. So our total load requirement is 11.1 megawatt, but in base case we just serve 3.9, and we have to shed 7.2 megawatts. So definitely the EV support or the EV fleets work in very better way. So if I show you through this, so right now in the crisis scenario, our total load served is 11.145, which is actually we have to serve. And here the load shedding, in load shedding case, we have just served 3.9 we have served, and this load we have shed. Just like here you can see we have to shed 7.216. But in EV V2G support EV fleets, our total load served 11.145, and how much load our EV fleet support, that is 7.618. So that's how this will work. And now let me for further explanation, now let's get into the MATLAB files. So I will show you how all this project work together. So here in IEEE 33 bus system we have our line and load data, and we have to calculate the branch matrix and all other stuff. So the next file here is run radial power flow, and this is the calculation file where we have utilized the forward backward sweep algorithm. And why this algorithm is adopted, because the Newton-Raphson method we can use, but Newton-Raphson method is not good when our voltage drops too low in which are appear in our case. So that's why we have used the backward forward sweep load flow, and all the load and resistance reactance are converted into the per unit. And next is just the load flow calculation and total loss calculation. So the next file is the calculation of voltage sensitivity. So in this file, which actually a bridge between the optimization and the load flow program. So the optimization part which we have adopted is the successive linear programming adopted. So this file voltage sensitivity, so this is actually a bridge between the optimization and the load flow. So the here the main logic I just write over here in this program. So the loop inside this program here is we have to actually cut our 1 kilowatt in our first scenario, which is scenario A, where we have to cut our load about 1 kilowatt. So each cut of 1 kilowatt actually change in form of this Jacobian matrix. So if, for example, if we cut 1 kilowatt at bus 18, the voltage at bus 33 will rise by the 0.005 voltages. So that's how this all process will work together. And the next one is which is the final file, is the main voltage recovery pro.m file. So here in this file, initially I just set up the variables. So here is the second case where we have to shed our load. So initially we set our parameters, then this is the main loop. Here let me start debugger here, let me click run, and here our minimum voltage target, which is our safety limit, is 0.9. If our minimum voltages, which you can see that we have calculated using this load flow program, the voltages at each bus. So we just calculate the minimum voltages that appear across the 33 buses. So if our voltages appear across each bus is greater than 0.9, then we have to break this program and break this loop, and we have to jump into the next step. But meanwhile, until this process succeed, we have to repeat this loop. So if I let me show you, here you can see that we have minimum voltages appear are 0.5589. Let me click on continue, and right now we are going into 0.8869, which will appear next over here. So, and next if I click once more, we have, let me click another here, let me click on continue. And so for the fifth iteration here, let me show you. So that's how we have actually the 5 iteration, and we just got improve ourselves from 0.89 to 1. So in the 4 iterations, we just improve our voltages from 0.5589 minimum to 0.8921. But we can still improve. But for this program, for the sake of the simplicity of this program, we just assume the 5 iterations. So now we are out of this loop. And meanwhile, inside each iteration, we have updated our variables, so we get the best. Voltage at the output. And next, there is the minimum load shedding. We are out of this, and this is the now we are into the AB fleet sport. So in this we have the same procedure same function, but here the optimization program is work this command. So linprog, so how it is does it work? It's actually work on this way: ax is less than equals to b. So what's exactly the b? B is our actually represent here our the voltage gap between the 0.9 and 0.55. So that's how it works. And if I click on the continue, so let me show you again. So this way, here you can see that this is the V2G scenario, and from time to time we are going to improve our program. So this voltage profile was for the load shedding, where at this point our voltage again collapse below the safety limit, and this was the perfect scenario. So that's how I just explain this project in a very simple way and in a quick way. So if you want more depth analysis, you may write in the comment section, and I will make another video. Thanks for watching and have a good day.